Okay, so we'll get underway straight away. So the next speaker is Ryoto Tange from Waseda University, talking about L-invariants representations.
Thank you very much for the introduction. I'd like to thank the organizers for giving me a nice opportunity to talk in this workshop. Today, I'd like to talk about L-invariants or representations of total. So this is the contents of today's talk. So firstly, I will introduce myself, what I'm working on. In section 1, I will quickly review Hira theory, which is one of the famous theory in number theory. In section 2, I will introduce adjoint invariants in knot theory. Firstly, introduce myself. What I am working on is arithmetic topology, which studies number theory and knot theory. And I especially working on knot theoretic side. And I was a student. I was a student of Morisha Sensei, who is one of the organizers of this workshop. So this is a basic analogies between number theory and knot theory. I think this also appeared in yesterday's talk. And for important correspondences for today's talk is these two. The composition group over P in number theory corresponds to peripheral group of K, namely fundamental group of boundary torus, and monodromy and Frobenius over P respectively corresponds to meridian and longitude of knot K. In particular, there are close analogies between Iwasawa theory and Alexander theory. And most important correspondence is Iwasawa polynomial, namely algebraic periodic function in number theory corresponds to Alexander polynomial in knot theory. And note that the viewpoint of group representations, these two theories can be regarded as abelian deformation theory of group representations. So we would like to consider non-abelian deformation theory. So our aim is to fill the question mark in the dictionary. And in number theory, non-abelian deformation theory are only studied by Hira and Maser. And so we would like to consider the counterpart in knot theory. So in today's talk, we like to consider adjoint L-invariants in theory and investigate their topological analogs. For my previous works, we introduced with joint work with of course Morisha Sensei. For example, L functions, and also for SEMA modules for SS and also we studied some properties of L functions relating to A searches. So let me briefly introduce what's the L-invariant in number theory. So in number theory, Greenberg initiated the study the L-invariant for periodic periodic Galois representations, and he interpreted it in the context of Galois deformation theory. So let me briefly explain what's the periodic representation. Let A be the commutative ring with identity, and we say the representations of prime group to J2 J2A are periodic if the law restricted to the decomposition group simultaneously triangular matrices, and observe that by considering these two this dictionary in not theory we can observe that the representation from not group to S to C can always simultaneously equivalent to upper triangular matrices. So let me continue the introduction. So for a given periodic modular P representation, rho P bar from prime group to G to FP, FP is a finite field. Here produced the periodic modular universal deformation board rho P from prime group to G to board rho P bar, where this ring is a big complete local ring. For example, the power series with coefficient periodic integers. For periodic Galois representation, rho P from prime group to G to CP, here propose the L-invariant for adjoint representation. So this is a summary of today's talk, and right-hand side is the answer of today's talk, and I will explain this more precisely. So in order to define L-invariants, we need to define deformation of representations. So in our study, let G be the prime group and K be the finite field with characteristic not equals to 2, and O be the complete discrete variation ring with the distributive K, and rho bar is prime group to representation from prime group to G to K. And we call the pair R rho deformation of rho bar if R is complete local origin with the distributive K, and rho is the representations from prime group to R with rho modulo max ideal of R coincides with rho bar. In particular, if rho bar is periodic representation, we call the pair R rho periodic deformation of rho bar. If R rho is a deformation of rho bar, and rho is also a periodic representation. So for simplicity, let rho bar is a periodic representation, and we call board R rho bar board rho universal periodic deformation of rho bar if this pair is a periodic deformation of rho bar, and for any periodic deformation of rho bar, there is some morphism from both are lower to such that the composite of psi and dysmorphism and Baudrillard are strongly equivalent, namely quite stronger than just taking the conjugation. This diagram is summary of universal deformation. And we call this ring universal p-ordinary deformation of low bar. And the existence of universal p-ordinary deformation of low bar is known by Maser. If low bar is absolutely irreducible, namely low bar extended to K bar, where K bar is the algebraic closure of K is irreducible, and with some assumptions, we can say that there always exists universal p-ordinary deformation. So now we are ready to define L-invariants for Galois representations. So let low bar be the absolutely irreducible p-ordinary representation, and here both are low bar, both low be the inverse p-ordinary deformation of low bar. And for simplicity, assume this ring is equal to the power series with coefficient O. O is, for example, periodic integer. And let rho be the representation from prime group to J to O, which obtained by putting x equal to 0. And let adjoint action of prime group to be the conjugation. And we consider the map from C to C, from prime group to 2 times 2 matrices over O, such that G maps to the product of derivative of each entities, each entities of matrices, this is of image and the inverse of images, and finally put x equal to 0. We can easily see that this class can be regarded as one cycle, and by restricting this map to the composition over P, we can regard as upper triangular matrices with place equal to 0. So by using this entry, we can define finally L-invariant for adjoint representation. And important part is this fraction. Denominator is monodromy over P, and numerator is the probability over P. And we like to use the that dictionary. And this is some applications for elliptic curve. I'm so sorry, I'm so familiar with this, but note that periodic Galois representation attached to elliptic curve corresponds to holonomy representation attached to the complete hyperbolic structure. And there's some relation with some elliptic curve properties, for example, and these two are the main conjecture of adjoint L-invariant. And first one is the non-banishment of L-invariant. And the second one is the relation with derivative of algebraic function, adjoint function, and the adjoint sema modules. And we would like to consider these analog in knot theory. So next, let's introduce deformation in knot theory. So as before, we can similarly define deformation, universal deformation, and note that in knot theory, we often consider finitely generative groups. So for example, we often consider SS to K representation. This is a summary. And similarly, as in number theory, the existence of universal deformation is known by Mocha Sensei, Takakura, Terashima, and Ueki-san. That so similarly, if rho bar is absolutely irreducible, we can always say that universal deformation always exists. And in knot theory, we can easily consider example. So this is an example for figure 8 knot. We can like the group presentation explicitly, and we can find the representations explicitly. And we now consider it's F7 representation given by formulas. And by considering this representation over 7 addict integers, and by considering these entries modulo 7, we obtain the entries of rho bar. So we can say that the pair of this is a deformation of rho bar.
Sorry, on the previous slide for the representability result, are there any conditions on K? Is it not
okay? Okay, K is I think characteristic is not equal to 2. Yeah. Thank you very much. And similarly, we can consider universal deformation explicitly by considering the representation over several power series of several integer coefficient. And by substituting this matrices with x equals to -2, we obtain the previous G7 representation. And so we can similarly say that this pair is a universal deformation of rho bar.
Does universal mean that it contains all representations, or
Yes.
like a subrepresent? What is universal?
So this is a summary of so so we can obtain representation from is both rho bar and by substituting these values. With that, up to SA2 conjugation. Yeah. Sorry. So, and similarly, consider L-invariants. And so to consider explicit correspondence, we like to consider holonomy representation. So we consider hyperbolic not case. And especially attached to the complete hyperbolic structure. And we can regard this representation as SA to C representation or SA to FP representation. And we can always say that this representation is absolutely irreducible. So we can say this the existence of and so for P case and field case we can say that universal deformation ring can be obtained by coefficient GP. But in C case, we consider C H bar, which is non-commutative ring. But we are not we couldn't find the example of this CH bar. We have some difficulty of finding this. So for simplicity, we consider as in number theory efficacy and fields.
If you have other rows to like FP from a hyperbolic knot, do you have also still a nice form for this universal deformation ring?
Yes. It doesn't matter for holonomy representation. If representation is absolutely irreducible, you can consider universal representation.
Okay, it doesn't.
But so today's topic is to consider the L-invariants. So we like to consider holonomy representation. So as before in number theory, we can similarly define the L-invariant as by considering similar one cycle. But some small difference is that we substitute the value at the last. And the reason why I consider is the following next example. So as before, we can for figure knot case, we have this kind of holonomy representation, and for simplicity, we consider again finite field F7, and we consider this universal deformation of holonomy representation, and this is done by Ueki-san. And we can regard this as power series with variables x minus 2. However, by considering the eigenvalue, we must consider square root of x minus 2. So maybe we need some more rigorous arguments, but in I'm not going into details in here. So just by computing explicitly, we obtain one cycle image as the product of derivative derivative of eigenvalues times inverse of eigenvalues. So we can explicitly compute, and so this is why I said that substituting the value at last, that there appears some square root of x plus 2 in the denominator. So by computing at here, we cancel these denominators. And so finally, we can substitute x equal to and obtain the value 2 times square root of minus 3. And This is known as E-not cell cusp shape, which is also obtained by the image of longitude, and which is 2-1 entry of that matrices. And also this can be obtained by topological invariant called distortion, which is maps from non-abelian Z2C representation from GK to C. And this cusp shape can be written by this ratio, respected to the denominator is milliradian and longitude is numerator is longitude. And here we can regard that this cusp shape can be corresponded to Tate period. So this is conjecture of this, and the latter part is shown by so. And for the cusp shape, it is known that this values are always not equal to 0. So this is a first conjecture of as I mentioned before. And this second conjecture is due to Yamaguchi's result, which is result that the numerator of that function can be written by the limit, namely the derivative of this is Alexander invariant of not K. So this is a summary of conjecture. So we obtain this similar conjecture in not theory, not theory as in number theory. And in our previous work, we also obtained that these same modules can be regarded as distortion, respected to milliradian. Okay, so I'll stop here. Thank you very much.